This is my Getaway pinball machine. It was made in 1992 by Williams Electronic Games. You can see it's obviously car themed. There's a Lamborghini in the back glass. There's a supercharger blower in the back of the playfield. A stoplight in the corner of the playfield. And this big tachometer right in the middle of the playfield. The goal of the game is to cycle the stoplight from green to yellow to red and then outrun the cops. One of the cool features is this, what they call the supercharger in the back of the playfield, which has 3 electromagnets underneath this supercharger blower cowl that propel the ball around this metal track really quickly. I've got the machine in test mode so that I can show you how the supercharger works. See, when I activate the supercharger test mode, this gate will close, causing this ramp to change from just a loop like this to looping the ball around the track. So I'll activate the supercharger test mode. You can hear the gate close, and we'll throw a ball onto the track so you can see how it works. If we start up a game, I can show you how the tachometer in the middle of the playfield works. When I hit the flipper button, you can see the tach go up. And as I go around the orbits in the machine, if I can get it, the tach goes up and I have to use the shift knob on the front of the machine to shift to the next gear. Like so. I've already made a few modifications to this Getaway. I added the donut shop that shows up in some of the dot matrix display animations. I got that from muzzlemods.com. Added the mountain that was present in the prototype Getaways and was removed for cost-cutting reasons. Got that from pinballtoys.com. I changed the gas plasma dot matrix display to a more modern LED display that I got from xpin.com. But what I want to do next is add a real automotive tachometer. I've thought about tying into the most obvious choice, of course, is tying into this tachometer in the middle of the playfield, so that the RPM that's shown there is reflected on the physical tachometer. And I've also thought about tying into the optos that are all over this track to track the speed of the ball as it goes around the track, so that the tachometer needle rises either the faster the ball goes or the more loops that the ball makes around the track. Here's the tachometer. It's the cheapest tach that Autometer sells. It's from the Auto Gauge line. It's driven by these 4 leads. Black is the common ground. White controls the illumination. Red is 12 volts. And green is the signal line. Pulses on that signal line cause the tach needle to go up and down. You can see this tach tops out at 8,000 RPM. Right now I've got it configured as a 3-cylinder engine, which means it's expecting 2 pulses per rev. Ideally we want 266 pulses per second to make that needle go to 8,000 RPM. The first circuit is, I think, the most simplistic circuit you can make to drive this tach. It's running on 12 volts. It's based on the 555 timer. I've got a 0.33 microfarad capacitor. R1 is 1 k ohm. R2 is 10 k ohm. Here's the signal line coming out of the 555, going through a micro switch to the signal line on our tach. So when I close the switch on the signal line, you see the tach goes from 0 to almost 7. So with this RC circuit, with the 0.33 microfarad, the 1K and the 10K ohm resistors, I'm getting a theoretical pulse of 208 Hertz at the 50% duty cycle. Ideally we want 266 to get that needle to go to 8,000 RPM. So we're running 208, and that's why we're a bit short. Phase 2, still using the same tach, but I've stepped up the complexity of the rest of the kit significantly. This is the basic stamp development board from Parallax. In phase 1 I wanted to keep things as simple as possible, so I just used a 555 timer, but that didn't give me a whole lot of control over what I could do with the tach. I've been wanting to take a look at microcontrollers for a while, so I stepped it up. So this kit uses the Parallax Basic Stamp 2 microcontroller, which is right here. The board runs on 12 volts. That's stepped down to 5 volts for the microcontroller. I'm using both 5 volts and 12 volts in this circuit. So we've got the micro powered off of 5 volts. It emits a 5 volt pulse over this line, which goes to this micro switch. This transistor steps it up to 12 volts. This is our 12 volt rail here. The tach is powered off of 12 volt, and the signal line of the tach comes off the transistor. So in the previous scenario, the 555 was generating the pulse. Now the micro is generating the pulse. So I'll fire up the board. Micro is already generating the pulse, but the switch is open. When I close the switch, you can see the tach goes up to about 4K and sits there. Right now the micro is generating a steady pulse. It'd be really easy for me to change that in software. But unfortunately, I ran into a snag. This microcontroller is just not fast enough to generate a 266 Hertz pulse and have code that is controlling the speed of that pulse. So I can generate a pulse that's pretty quick, but I can't have any weights in between. I can't have any logic in between. About as fast as I can go with logic, is something like this. So it's back to the drawing board. It took me weeks to figure out what to do next. I had to put away the toys and start looking at data sheets and drawing up circuits. Mostly data sheets. I knew I wanted to stick with the microcontroller because it gave me a lot more control over what I could do with the TAC. But the controller just wasn't fast enough. And I already dropped a couple $100 on it, so I didn't want to put any more money into a faster microcontroller like an Arduino or something. So I started looking at ICs that can maybe offload some of the pulsing, so the microcontroller could control it, and another chip could pulse faster than the microcontroller could actually pulse. That led me to voltage-controlled oscillators, like XR's XR2209. So this guy can pulse between 0.01 hertz all the way up to 1 megahertz. All I need is 266. His pulsing and the frequency is controlled by a resistor. So if you change the resistance, it'll pulse slower or faster. So so I've got a way to change frequency and to pulse faster than the micro can. Then I needed a way to change resistance programmatically. So that led me to digital potentiometers, like the microchip MCP41100. This guy uses an SPI signal to change resistance. The 41100 can change between 0 and 100 k ohms. The only thing that sucks is the XR chip if you run it at 5 volts, needs split voltage, so it needs a positive 5 and a negative 5. You can run it at 12 volts, and if you run it at 12, which would actually be ideal for me because the TAC runs at 12. If you run it at 12, you can just use a single supply, so just positive 12 volts. The problem is the microchip chip can't pass 12 volts because it runs on 5 volts. And if you pass 12 volts through it, it'll burn it up. So I had to run at 5, which means I also had to look into split supplies. I ended up just buying one. There's a cheap little board. It was like 20 bucks. That's pretty small. That'll give me +5 and -5. So I'll have to run +5, -5 for the XR chip. I gotta run 12 for the TAC. I'll just run the whole thing off 12 volts. It took a really long time to figure out what resistor and capacitor to use for the XR2209. I've got a sneaking suspicion that the formula I'm using isn't the whole story, and I might be way off, but time will tell. There's this graph that shows supply voltage versus timing resistor values and what the acceptable operating range is. So we're running split supply at 5 volts. And I ended up choosing a resistance value of 7,150 ohms. So at 5 volts, it's right down at the bottom. Well, I hope it works. So I arrived at that value through trial and error and use of my trusty TI-82 calculator, which I haven't used since college. So that's 470 milli, micro, nano ohm capacitor, timing capacitor, with a 7,150 ohm timing resistor. So resistance and frequency. So if I knock the digital pot down to 0 ohms, I'm getting 297 hertz, which is just a touch above the 266 ideal value. And as we ramp up the resistance to the 100K that it tops out at, we're at about 20 hertz. So at the bottom end, I think we'll be sitting at about 600 RPM. So in between the 0 and the 1 on the tack that's measured in thousands of RPM per minute. Well, I hope it's right. I'm kind of thinking it's more complex than that little formula. The data sheet's not really clear on that. But we'll find out. Here's my first attempt at a circuit that brings all of this together. Here's the tack signal, the voltage controlled oscillator, the digital potentiometer, and the microcontroller. The tack signal is pulled up from 5 volts to 12 volts and is grounded when the voltage controlled oscillator pulses. The voltage controlled oscillator is configured with a 470 nanofarad capacitor and varies its oscillation frequency when the digital potentiometer changes the resistance on this line. The digital potentiometer is configured programmatically via an SPI connection by the microcontroller. This 7,150 ohm resistor makes sure that when this digital potentiometer goes down to 0 ohms, we don't pull too much current through this and blow it up. Several parts orders later, I'm back with the next phase of my tachometer project. I'm pretty excited about this because this is it's some real progress. This is probably a good time to mention that the idea from this came from a fellow Pinside member, Hooked, from Hooked on Pinball. You can see his info there. He came up with the idea to hook up a tachometer to his Stern Mustang pinball. He's got a video of how it works posted on YouTube.
Here's how it works. Basically, you hit your spinner, and your RPM increases. As it slows down, of course, your RPM stops.
My guess is he's got a 555 hooked up to the contacts of that spinner switch. So when it makes contact, it begins sending the pulse to the tack. I wanted to go a little bit more complex than that, especially because I don't have a spinner to tie into on Getaway. So here's where I'm at. Schematic is unchanged from last time. I've started to implement this section of the circuit. So I've got the voltage controlled oscillator and the transistor that sends the 12 volt signal to the tack. I've delayed implementation of the digital potentiometer and the microcontroller just to prove that this portion of the circuit works and that I got my calculations correct. So here it is. This is the plus minus 5 volt board that I ordered from FutureLec that converts 12 volts to plus and minus 5. That's mainly to drive this voltage controlled oscillator. It's the XR2209. That requires plus minus 5 volts. So here's the VCO. Here's the transistor. This development board from Parallax runs on 12 volt. So I'm feeding 12 volts to the ±5 power supply. It sends out -5 on the yellow wire, +5 on the red. So I've got a -5 volt rail here, +5 volt rail here. And of course we've got our tach. So the digital potentiometer is going to end up going there. Like I said before, I didn't hook that up. So I'm using one of these 10K pots that's built into the Parallax board. My digital pot will end up being variable between 0 and 100K. So 10K isn't quite the range I need. But it definitely demonstrates that this works. It proves the concept. So let's fire it up. You can see the tach needle is at about 3¼ thousand RPM. And if I vary this pot closer to 0, it maxes out. Trim it back down to 10K and we're back to 3¼ . So I'm pretty excited about this. It's been a long time coming. I'll be back later with more. Made some more progress today. I added the digital potentiometer to the circuit. That's controlled via this 3-wire SPI connection to the outputs on the micro. So the micro provides a chip select signal, a clock signal, and a data signal. It sends a 1-byte command and a 1-byte resistance level to the pot. And that controls the resistance seen by the timing resistor connection on the VCO. We can fire it up. See, the tach goes almost through its entire range. It gets down to about 1. That's because of this current limiting resistor that's necessary to avoid burning this guy out. Something's wrong though. It's supposed to have, the digital pot's supposed to have 256 levels of control. But I can only exercise about 17 of those. If I try to increment from 00 hex all the way to FF hex, it seems like the first nibble is kind of ignored. So I don't know if something's going on with the way I'm sending the data, or if I've misunderstood the spec sheet. But I am able to get the tach to go its full range. So because of the way the code is interpreted, you can see that's the code I'm sending to the pot. I'm not exercising the full range from 00 to FF. It only seems to pay attention to that least significant nibble, except for around the full value FF. It'll catch that one. That's weird. So the code's pretty simple. Those are the pins, the 3-wire SPI pins I'm using. That's the command. The first byte to the pot is a command to set the resistance. So that's the command. And then I've got an array of what I've just through experience and trial and error, have found to be good levels to set the resistor to. And then I just walk up through that array and then walk back down again. So, pretty cool. I hope to figure out what the deal is with it not letting me use 256 different values. And if I can do that, then I can have a lot more fine-grained control over what I'm displaying on the tach. But this is definite progress. Pretty cool. I talked last time about my lack of fine-grained control and how I can hit the full range on the tach. But I've only got like 7 or 8 different steps I can use. The digital pot has 256 steps. That's why I bought this one. So limiting it to 7 or 8 is a bummer. It's been bugging me. So I thought I'd show you the behavior. I've changed code. This little program just iterates through all the different steps on the pot, up from 0 to 255 and then back down from 255 to 0. So it's already programmed in. I'll show you what it does. And you can see the needle bouncing. The needle actually bounces every time that second nibble hits 0. I'm not sure if I can show them both at once, but they're pretty hard to see. Anyway, and you can actually see I'm measuring voltage between this resistor through the digital pot to the VCO. Over here. Resistor, pot, to the VCO over here. And you can see, indeed, when the needle bounces, the voltage is oscillating the same way. What's interesting though is the resistance doesn't do this, just the voltage. Let me hook it back up and to measure resistance. Let's disconnect this. And we'll run just the pot. I'll disconnect from any voltage so I don't blow up my expensive meter. Yep. Alright, so now when we run should be able to see the resistance changing as we would expect. Don't want to blow up the meter. That should be good. So it's going to go all the way from 0 up to 100K. And you see, before we were seeing oscillations, and here we're not. So without pulling any voltage through it, aside from the the meter voltage, the pot's behaving just like I would expect it to behave. Anyway, it'll go all the way up to 100. Oh, that was fun. Yeah, so it's not the pot's fault. I think the pot's doing its job. The mistake actually was, of course, probably me. Because you can see in my original circuit, there's the pot, focus. And I'm pulling -5 across those resistance terminals. -5 volts. And the pot itself runs on +5. If you take a look at the spec sheet, it's the spec for the MCP 41100 is what we're using. It makes pretty clear that the voltage range across the resistor terminals is 0 to VDD, so 0 to 5 volts. I'm pulling through -5. So maybe that's the cause. I don't know. So I went back to DigiKey and ordered another part. This one's by Intercell. It's the X9C104 is what I got. It's another 100 kilo ohm digital pot. And this one advertises support for, where is it? -5 to +5 volts across those resistor terminals. The drawback is, on the microchip pot, I can direct access any of the levels from 0 to 255, whereas on this pot, I think there's only 100 steps on this, so I've only got 100 levels I can select. But the bigger difference is I can only increment or decrement, so I can't go directly to a value. I'm going to bump it up or bump it down. But if I can get smoother needle flow, it's a good trade-off. So those parts are on order. We'll see what happens. I've made some code and circuit modifications while I wait for my new potentiometer to come in. In addition to the 3 SPI pins that I had declared previously, I've added 2 new pins. One for the switch that the ball will trip in the machine, and another for a test switch that I'll mount external on the project enclosure. I've added some code to check these switches. And also some code to raise and lower the tachometer needle when the switches get tripped or don't get tripped. We can see it in action. When I turn it on, you'll see the tach enters a test mode. We can do it again by hitting the test switch. But what we'll actually see happen in the machine is the ball will cross the ball switch and cause the needle to rise. If the ball crosses the switch rapidly, the needle goes higher and higher until it pegs out. And then it will decline slowly. So if the ball's at a constant speed, it can hold the needle pretty steady. The tach's pretty notchy right now. That's why I need that new potentiometer, so I can have better control over it. pretty cool. I've got my new pot installed. This is the Intersil X9C104. You can see the wiring has changed a bit from the old pot. The old microchip pot was more sophisticated because it allowed direct access to each of 256 levels of resistance. But unfortunately it was limited in its voltage range from 0 to +5. And I'm passing -5. So this new Intersil pot has 100 levels of resistance, and they're iterative. So if I'm at resistance level 0 and I want to get to level 50, I've got to go through 1 through 49 to get there. That's generally okay because I'm working with a dial, so I don't need to jump to one point. I really want to go smoothly there. So it's alright. As I said, the wiring has changed a little bit. It's still a 3-wire interface, but the pins are a bit different on the Intersil. You can see we've got a chip select still. Then there's an increment pin and an up-down pin. And there's several diagrams that show how this works, like that one. But my favorite is the most succinct one. This one. So you can see when the chip select is low, setting increment to low moves the resistance up or down depending on if the up-down pin is high or low. I've got a little program that exercises this already loaded on the microcontroller, so we'll fire it up and see how it works. So this program allows me to walk through each of the 100 levels of resistance. Gotta tap pretty fast at the bottom. We'll talk about that in a second. But now you can see the needle start to move up every time I tap, incrementing through each of the 100 levels. Go back down. All the way down. So you can see the response isn't linear. I've got to tap a lot at the low end of the resistance range to get the needle to move at all. That's not the pot's fault. That's non-linear response from the voltage-controlled oscillator. I graphed it out on my trusty old TI-82. So there's the resistance formula. There's a lot of glare. For the VCO, that's Y1. Y2 is the minimum pulses per second that we've got currently, and Y3 is the max. So if we're at 266 pulses per second, then we'll be at right about 8 on the dial. If I graph this out, X is resistance, Y is pulses per second. You can see at the bottom of the range, in fact for like the first half of the range, we barely changed resistance at all. That's why I had to tap so many times, because I was moving up this direction. And then once we get about halfway, it starts to make a difference. And then towards the end, a single change in resistance results in a huge change in pulses per second. So there's of course some stuff I could do on the VCO, changing the resistance, the timing resistor, and the timing capacitor, to make the range more usable. But for now, I think I'm going to leave it the way it is because it's an interesting program. programming problem to make it look linear. So there we are. I'll do some more playing with the code to see what I can come up with. I've made some changes to deal with the non-linear response of the VCO. The circuitry is the same, but the code's changed. You can see I'm defining an array of 15 elements that span the entire range in resistance from 0 to 99. Each element of the array defines a number of steps offset from the previous element. So we start at 0, at position 0. Then at position 1, we're stepping up 45 steps. That large step from 0 position to 1 position helps deal with the lack of response at the low end. So you saw before that I had to click on the button lots of times just to get the needle to move at all. So that's automating all of those button taps to make the needle move the first time that I hit the button. So you can see that as we go to higher positions, we're taking less steps in resistance. So we'll walk through the code. I'll take you to the subroutines first. So one of the first things the code does is run this initialization routine. Since all we can do on a digipot is step up resistance and step down resistance, I really don't know when I start up where I'm at in the resistance range. So the first thing that I do is step up resistance all the way until the 100 levels, so that I know I'm at the top of the range, and then I back it back down 100, so I know I'm at 0. So you'll see the needle rise from its power on position up to 8,000, stop, and then go back down again. So that's my calibration and initialization step. Then I've got a few subroutines below to increment the resistance up or decrement it down, and both of those routines use this send routine that sends the command to the pot. So up in the main loop, there are 3 different major sections. The first is checking what I've called the ball switch. So that's the button that you'll see me tap to raise the needle on the tack. The second section is the check for test. So if I tap the other button, it recalibrates the needle. That's running that little routine. And then the last one, what I'm calling decline, is what gets run if no buttons are pressed for a certain duration. So you'll see when the needle goes up when I'm tapping the button. If I don't tap the button, the needle falls slowly. So there I'm trying to simulate how an engine would slowly decline in RPM when you let off the gas. So let's fire it up and see it in action. First thing it does is run its test cycle, like I said. And I'll tap the button and you can see how linear the response is. So we've got 15 positions on the tack. Stop tapping and it falls down again. kind of unfortunate that I've only got 15 usable positions. But if you remember from when I was showing you the tack on the playfield, there's only 12 lights that light up on the tack. So if I tie into the playfield tack, I'll only need 12 out of my 15. If I hit the other button, I can cause it to do a test cycle again. So it ramps all the way up and then falls back down again. So I'm pretty happy. Next step, I think, is to fabricate some circuit boards and figure out how I'm going to tie into the pinball machine.
Dispatch, this is 504. Suspect went in a red light. Over. Roger, 504.